So what I was hoping to do today is I'll actually talk a little bit about two different topics. One is about link analysis, which is page rank and stuff like that, which you have heard before. But I still thought it may not be a bad idea to just talk about it a little more from a slightly different, maybe a little more pictorial perspective, although Professor Santanam did talk about this in good detail. I'm hoping it'll still be useful in terms of understanding it, and some things, where repetition, it doesn't hurt. So I thought I'll include that a little bit. The second thing I'm going to talk about is graphs with plus and minus edges. Again, something which Professor Siddharth Sinha talked about a little bit, but he just talked about, that there are these graphs and all, and hopefully I'll talk a little bit more about this topic as well. So this is what I've chosen to talk about today. Okay. All right. So we're going to talk about searching the web, right? First of all, I need you to take, again, back a little bit into the history so that you appreciate why this is a hard problem, right? All of you, most of you are probably born after the, after not only just after the World Wide Web, but even after a lot of other companies have already been around. So think about it, that if you have lots of newspaper articles, papers, legal documents, you have different formats, text, PDF, docx, keynote pages, whatever. And so there are lots of different sources which are written in different formats, and often there are lots of, synonyms, right? That some words, a single thing will have multiple words of saying it. And sometimes, of course, you'll have one word which, when you say Jaguar, do you mean the car or do you mean the animal, right? So when you think of the early days of the web, I want you to go a little bit back and think of the early days of the web, where people are just writing, whatever they like on their web pages, and we have to make sense of it, right? And what makes it further hard, right, is the fact that people are writing in their own styles. Now, ever since the World Wide Web, everybody has become a content creator. Previously, if people were, writing articles for the newspaper, they were all trained in journalism. They are, for better or worse, at least everybody has some common denominator of training. They are writing the stuff. Now, here, any kid, whether it's age 7 or a not so kid, 70, can still go and write in their own style, right? And some of them are experts, some of them are novices, and of course, the content is changing. Okay. So this was the deal, right? And what happened was that in circa 2001, when people searched for World Trade Center, most of the things on that day, the results were not good, right? You remember the sad case of the bombing, right? Why? Because this thing was quickly changing stuff. There's a new event that happened today. It's very clear what is news versus what is web, what is images. You get all these tabs in a typical search engine. But think of the early days where people are typically just making content which they expect not to change often, and then somebody just searched for the web for an event that had just happened very recently. How do you do that? Okay. First of all, the fact that you have this web, that means you need some kind of algos which are going to crawl the web. Again, these are terms which you understand today, but imagine in those days you would have something that would crawl the web, and the web was still large, and how long would it take to crawl, and how long would it take to update your whole thing? So, right, so if you look at old search engines, Lycos, Yahoo, Alta Vista, there were many others, some of them don't even exist today, the companies, right? They vanished. So new search features were added later, right? And today, of course, you have WhatsApp, Twitter, and all of that, and that kind of really fill the gap. And very often, at least I receive, like a breaking news item, I receive it on WhatsApp myself. Okay, so now of course things have changed, but I want you to appreciate the problem of why searching the web is hard. Yeah, you have to crawl every web page. You have to identify the keywords. You have to store the keywords. You have to index them, so that when you see a keyword, where do you go, and all of this, right? So that's what it is. Now, in some sense, in the olden days before this, you would actually go to the library, and there used to be these index cards. I'm not even sure how many of you have seen a library index card? Okay, at least some of you have, right? So if you go walk into the library, then there is like this little square drawers which you pull out, and OP and PQ and all that, you go and look, and then that's when you go and find the book that you want, right? That's gone. So what happened was that we've shifted from a problem of, and you've heard this many times, of scarcity to the problem of abundance. So now you have a different problem. There's too much stuff. A lot of it could be noise from your perspective, and the catch is you need to find something which is not noisy from there, right? So how should a search engine be smart? How can a search engine make a decent recommendation? Right? Now, one of the things that people realize, so when people were looking for, when search engines were looking for, okay, how do I decide whether this page is good for this topic? Okay, so let's say if I'm looking for bipartite graphs. So we look for those pages which have the term bipartite graph mentioned in them. And I will see how many times is that term appearing on that page. If it's appearing 50 times, maybe it's a better page than something where it's appearing 20 times to somewhere which is appearing 2 times. Okay, so this sounds like a reasonable strategy in the early days. Now, if somebody realizes that this is what search engines are doing, then what they did, to spam it, they would just put the word bipartite graphs 5,000 times. Right? They could even put it as hidden text or whatever, so that if you're crawling, you'll think, oh, this is an important page, you'd rank it up, got a problem. So what then people notice is that that's one part. The second part is, suppose you have IISc. So IISc is a website. As a whole, it will not contain the word IISc millions of times, right? But any other page which has text IISc will point to IISc. So 2 parts. Number 1, that the text that is within a page may not often be the best descriptor of what this site is about. Rather, the terms that are being used to point to it may be better indicators. Of course, anybody who has a link to IISc will write somewhere the text IISc, and then it will have a link to iisc.ac.in or whatever, right? So, all right. So, okay, so those are the 2 points. Now, so the first point we are making is that, look, so links are essential to ranking. That means if different people are saying that this page is IISc, that's a good way of, that's a slightly more reassuring way, because multiple different people are saying so, rather than what I'm just writing on my own page, right? All right. Yes. So, sorry, say that again. How are they saying? Because the text will say IISc, but the hyperlink will point to ac.in. Right? Or they may say that, oh, here you can go to the page of IISc and then there'll be a link or something. So there'll be like some descriptive text very close to the link, if not in the link itself, that might give us this idea. Okay. All right. So now let's say that somebody gave a query called newspapers. Okay. Now, and so what I did is I'm seeing how many people are calling the San Jose Mercury News a newspaper, how many are calling the Wall Street Journal. Can you see these things clearly? Yeah. So for example, San Jose Mercury News got 2 votes, Wall Street Journal got 2 votes, New York Times got 4 votes, and so on. And you can see, interestingly, Facebook got 1 vote, Yahoo got 3 votes, and Amazon got 3 votes as well. Right? Now, how do I decide what's good? This seems to suggest that Yahoo is a better source of a newspaper than Wall Street Journal is. Clearly, that can't be correct. I think we'll all agree that it's not correct. Yeah?
Even the websites which are pointing towards, if they are pointing towards more authorities, then they become more important.
So these terms, I don't know what you mean by authority. I've not yet said any term like that. So, but yeah, what you're saying is true, and let's see how we get there. Yeah. So what did you do? We enter 1-word query, we call newspapers, right? And we see that some of them are bad, some of them are good, right? So by this voting mechanism, we can get at least some idea, okay? But But look at it like this. Just like something is a good or bad newspaper, similarly, the other set of guys is a good or bad source for pointing to newspapers, right? So, so if I look at, so intuitively you'll see this, and we'll see this more precisely also, but if you look at this guy here, he seems to have a much better idea of what newspapers are than, let's say, this guy. Would you agree? Right? So somehow we should fold this into the calculation, as to who's a better guy. But it's newspapers, so you and I know what newspapers are, good and not. But what if it's a topic about which I am completely clueless? I don't know which is a good recipe site and which is not, or which is a good Bharatanatyam site or not, or I have no idea, right? So what do we do? So we say, look, we are trying to identify good newspapers. Let's also try to identify good lists of newspapers. Okay? So we say, okay, let's extend our voting scheme in the following manner. So what I'll do is that all the votes that the newspapers have got, right, I will transfer those votes to all the websites or the pointers that were saying these are lists of newspapers. Okay. So what I'm going to do is this. So if I look at this guy, the top guy, this guy is 8 because it's 2 plus 2 plus 4. So the thing that it voted were voted for by other people, and now the total votes of the things it voted got 4 plus 2 plus 2, so 8. Right? Similarly, this guy is 11, this guy is 3 and 3. Do you get what is going on? Right? What is happening? That's this slightly, previously everybody was the same for us, but now slowly they are becoming clear as to who's above the other in terms of being not a newspaper, but a list of newspapers. Yeah? So I know that somehow maybe these guys are better. So of course I can do a very smart thing, which is now I take these and these become the weight for these guys, and then I transfer them back to the newspapers. So now which was getting just 8 votes, now look at San Jose Mercury News now gets 11 plus 8, 19, Wall Street Journal gets 19, New York Times gets 31, and look at these guys thankfully now have dwindling scores in comparison to the other guys. Right? Okay. So now what we are doing, we are toggling between giving values to newspapers, transfer them to giving values to lists of newspapers, back to newspapers, back to lists of newspapers, and so on. And of course, the fact that why should I stop here? I can keep doing this. I can keep doing this till it gets refined. Yeah, I can keep doing this till it gets refined. And this is called, of course, the principle of repeated improvement. Yeah? And you saw this in the form of a very neat, short, succinct mathematical expression that Professor Sundaram showed the other day. Okay? All right. So now just to define the term that Poojan used. So the pages that we are originally seeking, which are supposed to be experts on a topic, are actually called authorities of that topic. The lists guys, the other side of the guys, they are called hubs. Okay, and this work was done by Professor John Kleinberg, yeah, and of Cornell, and he wrote this paper roughly the same time around which the paper from Larry Page and Sergey Brin on PageRank appeared. Okay, so these two concepts are not the same. They are closely related, and we'll talk about the PageRank in just about a few minutes. Yeah. When do we stop this? Yes, and this is exactly what we'll answer in a few minutes. Yeah. So yeah, let's get that first. Okay, when do we stop? Yeah. So for each page P, we are trying to. So now what we are saying is, for each page P, we are trying to estimate how good. See, I don't know about any topic. So the fact that something is a list for newspapers may also be an authority on something else. I don't know. I'm not an expert on all these topics. So what I'll instead say is, look, for every page, I'll think it's an authority of something and it's a hub for something else, right? So I will assign two numerical scores to each page. I'll call it auth P and hub P and initialize both of them to be 1. Okay. Then what do? Then I'll have an update rule. For each page P, I'll update auth P to be the sum of all the hub scores of the pages that point to it. Then sequentially, I'll say for each page P, update hub P to the sum of authority scores that it points to. Right? So I'm first going to do all for this, then all back to this. Yeah? Sequentially, one after the other. All right. Now we'll choose a number of steps K to Sharon's point. We choose a number of steps K and we'll say, look, we'll do this only K times because that's all the time I can afford. And that's what I can do. And then first I'll apply one, then I'll apply the other and keep doing this. But what happens is there's a technicality that these numbers may become very large. So we can normalize them by dividing them all by a decent enough denominator so that the numbers don't become too big to handle. Yeah.
How is K chosen?
Yeah. So so one is K that you can choose either by experience, or sometimes you may say, look, if the values are not changing by more than 0.001 between two iterations, I'll stop. Or 0.000001, whatever you like to choose. Right? So it's really up to you. We are doing both of them one by one. It doesn't matter which one you choose first. It doesn't matter which one you choose first, right? But the natural thing was to probably see that first look at the pages that were, first look at the authorities because somebody voted for them, so I get a natural voting there. So maybe that's why it's a natural way of doing it, that, right? But in some sense, it doesn't really matter. But otherwise, you won't get toward the lists. Think about it. See, okay, let me answer that. So, oh, wait. Did I answer your question? Or did I say the opposite once again? So, authority update. Yeah, see, because, okay, why am I doing the authority update rule first? Let me do that. So, look at this page, right? So, here what happens is, I don't know, I first need to go on the authority side just to see how many votes they are getting. Only then can I transfer back to the hubs. That's why I'll rather do this first. Yeah. Right. So how do I normalize it? I divide each authority score by the sum of all authority scores and divide down the hub score by the sum of all hub scores. That's why I'll keep things in control. Right. And these are the normalized values, and things are looking better now. The so-called better newspapers, at least as far as we know, they seem to be coming up towards the top, and the bad ones are going down. Okay, sorry about this. Then there's a limiting value. Yeah, that works. I'll clean this up, guys. Sorry, but you get the idea, I hope. Right? They will actually converge as k goes to infinity. And this is sweet, right? It doesn't matter with what values you start. Thankfully, everything will converge to the same thing, and that's a blessing, because then you know that this will work. And of course, we want all of these to be positive. I'm sorry? Why are they converging? I think this comes from the. I'll check this, but I think it's coming from the theorem in linear algebra, right? That if you have all of these things as positive, then it will. Okay, so just hold on to this thought. Yeah, I'll come to this in a bit. So, Peron Frobenius, yeah. I think that's why it may be happening, but let me just check that. I'll check that afterwards. Okay.
We can represent these equations as finding the eigenvalue of a matrix. If A is the adjacency matrix, the vector for the authority scores and y is the.
And you're keeping on doing it, right? So that's,
So
yeah.
we'll get that if A is the adjacency matrix, then we are finding the eigenvalue of A transpose. So if it exists, then it will.
Yeah. So here is the relative stuff. I mean, here's the very closely related stuff, which is page rank. Yeah. And a page rank is slightly different from the paper of from the ideas of Kleinberg, where he separated things into hubs and authorities. Here he said, I'm not going to have two things. I'm just going to have something called page rank, and I'm going to be only interested in links. Now you all know the story that Brin and Page were Stanford PhD students when they thought of this idea with the professor, right? And they had this. This became a patent that Stanford owned, and they wanted to sell this idea to Yahoo. So they got into a discussion with Yahoo, but Yahoo did not agree. They could not settle on a price on what this patent costs. So then these guys, since they didn't agree, so they said, okay, look, we'll go and start a company of their own. And then many years later, Stanford sold that patent and made a lot of money. Yeah. So that's the interesting part of the story. Okay, so now very closely related notion is page rank. A page is important if it is cited by other important pages, right? And this is we discussed the other day also. Yeah, there is a circular definition. How do we know something is important? Well, if it's pointed to by important pages. But luckily, when there is a circular definition, we can keep iterating and clarifying it. Okay. So, all right. So it's like saying that if somebody is getting a lot of inlinks, then that page is important. But how important is that page? Just like we went to hub scores and said, look, this is a better hub. Just like that, if the page you have an inlink from, if that fellow is more important, it's like, think of it, you're getting recommendation letters, right? Either you could be important because you're getting 100 not so significant recommendation letters, or you're getting this one rocking recommendation letter from a star, right? And of course, it would typically be a mix, and we want to make sure that this kind of gets calculated properly. Okay, so intuitively we'll look at this, and again, the maths of this is something that has already been described to you, but I'm only going to describe the process much more, a little more visually, and actually we'll do a detailed calculation to see that it kind of settles down in our minds. Okay, so what we imagine is that page rank is kind of fluid that circulates through the network. Yeah. And as it goes, of course, if a node has many incoming links, that means it's getting fluid from many places. So the fluid in this node is going to swell up. Yeah. If somebody has more outgoing links and few incoming links, then it'll dry up slowly, surely, right? So you kind of see that. Okay, now let's do this a little more exactly. So in a network, n nodes will assign the same initial page rank as 1 by n. That means initially, I want to be fair, everybody gets 1 by n, then we will start the process and see where it goes. And again, we'll choose a number of steps k, and we'll perform a sequence of k updates. Right? And what do? We say whatever this guy is, equally I'm going to divide to my outgoing links. I'm going to just fairly and squarely divide it to all my outgoing links. This is kind of different from what we did in the churn model, because there we knew this guy is talking much more frequently with this guy and less frequently with this guy. So the energy we gave out was in proportion to how much they were talking, right? So it's a little bit different. All right, so this is what happens. If a page has no outgoing links, it passes all the current page rank to itself. Okay. All right, and each page will have its page rank to be the sum of all the stuff it receives. I hope this part is completely clear. Yes? So initially I'll set everybody to 1 by 8. Yeah, because there are 8 pages over here. And we have to check at every step, just to be clear that we are not making any mistakes in our calculation, that everything adds up to 1 at the end of each iteration. Okay. All right. So now what you can see is B is going to get half of A. So I want you to, I'm going to do A the last, okay, just to make it easy and clear to see. Okay. So you can look at the formula on the left. So B and C are A by 2, because B and C are the only 2 outgoing links from A. Okay, and this is the initial picture, 1 by 8. So at the top, it's the initial picture. At the bottom, the values we are going to go, are writing, they are the output of the next step. So please watch out, okay. So B is A by 2, so B is going to become 1 by 16. Right? C is going to become 1 by 16. Is that all right? Right. So now, similarly, if you look at E and D, they are going to get half of what B has. So they will also get 1 by 16, E and D. You see that here? Right? Then let's look at F and G. They are going to get half of C. So they are also 1 by 16. Now H is going to get half of D and half of E. So why is it half of D? Because half of D is going back to A, half of E is going back to A, and D and E were, to begin with, they are 1 by 8. So it's going to get 1 by 16 plus 1 by 16, which comes back to 1 by 8. So H actually still keeps 1 by 8. Guys, are you following? Yeah. And A now is going to get all of F, all of G, which is 1 by 8, 1 by 8, all of H, and half of D, and half of E. So it has 5 incoming edges, 1, 2, 3, 4, 5. Right? So I can write A as F plus G plus H plus D by 2 plus E by 2. And that gets actually a value of, that ends up being hello. Now notice that, please notice, because this is the confusing part, that right now we have used all the values as 1 by 8 because, see, from 1 by 8 you calculate this, then don't take the new value of that guy. So in one iteration, keep it very simple, keep it very clear that we are using old values to get the first set of new values. Okay. All right. Okay. So that's done. Okay. So now the new values are this. A is half, B and C are 1 by 16, D is 1 by 16, and H is again 1 by 8, and this. And again do the same thing again. Okay. And of course I should make sure that after each iteration, the sum total still remains 1. So make sure that we've not made any mistake in the calculation. Just check that that's the case. Okay. So we do the process again, and you can see that A is at 1 by 2. Yeah, this is the previous one. And you can look at the numbers at the bottom. So B and C become 1 by 4, A becomes 5 by 16. Right? So its actually value has fallen a little bit. And G and E are actually 1 by 32, so they are even lower than this. Okay, let's keep going. Right? Now A is 5 by 16, 1 by 32, 1 by 16, 1 by 4, and you can see this, right? So intuitively looks like, look, A seems to be high in value, and B and C seem to be high in value. Why? Because they are being pointed to by A, intuitively, right? A seems to be of high value because it's getting stuff from a lot of other people, right? That's why A is important. B and C seem to be important that they are getting only from one guy, but that one guy seems to be important, that's why they are getting it. So that's what it seems like. The other guys, in comparison, seem to be less than these 3 guys. Okay? And again, we check that this is still, the sum is still 1. Okay? Okay? And we keep doing this, right? And this is kind of the equilibrium values we get. So A is 4 by 13, B and C are next, and everybody else is less than that. Okay, and that kind of matches our intuition. Okay, so this is the same page rank which you saw written as a neat succinct equation a couple of days back. Okay, this is how it actually works. Right. So they again converge to limiting values. Right. It's because of the theorem that this Perron-Frobenius theorem that will happen. So long as you have positive numbers in the matrix and you keep doing this, there's a guarantee that it will converge, always converge. So what we saw is that PageRank is never created or destroyed because we made sure that it was always summed up to 1. So we're not losing anything, right? Right, and of course once it's limiting, so you know that if you do one more iteration, it's not going to help because it's not going to change. So we are all good here.
Like if there is a node which has no incoming edges, then it's not.
Yeah, then it's not part of the game. It's not part of the game.
But it should be if it's like pointed to by a lot of important nodes.
If it's being pointed to, if there are incoming edges, then it becomes very important. And if there's no outgoing edges, that's fine because it's collecting all the fluid. So it becomes very important. That's what you're saying, right?
But I think what he was trying to say is that if that is the case, then the graph is not. Around Frobenius theorem's assumptions are not satisfied.
Correct. Right? So just hold on to this thought and question for a few seconds. Yeah. So if the network is strongly connected, then there is a unique set of equilibrium values. Strongly connected means what? That from every place you can get out to some other place, right? And every place you can reach every other place. That's the thing, right? Strongly connected in a directed sense, right? And so whenever the limiting PageRank values exist, these are the only values that satisfy the equilibrium. We are all in great shape and fantastic. Now, suppose we have a network like this, right? Which means that it's not really strongly connected because once I get into one of these F or G guys, there's no getting out. It's kind of what you were saying. You guys are saying. Right? Now what do we do? So what is going to happen now? First of all, why is this a problem? It'll kind of suck all the thing towards itself. Right? So if I knew that this is the way PageRank, so we're talking about spamming. So previously if it was text, I would write 50,000 times. I would write, bipartite graph and I would fool the search engines into pointing to me and putting me into high pedestal. Now, I can do this trick. If I know that PageRank is working like this, that I'll create 2 pages and I'm the creator of both of them, so I'll make them point to each other, no, not pointing outside. And I'll beg and request my friends or threaten them, please point to my page. And I will get all the PageRank to come to me. I can cheat, right? So we need a way out of this. Yeah. First, let me convince you that it will indeed suck all the values towards itself. Okay. So again, as before, all 1 by 8. That's the same thing we do. And these guys became 3 by 16. Okay. Notice that 3 by 16 is slightly less than 4 by 16. So you can see it's only second, F and G are currently only second to A. They are already better than everybody else. Okay. And eventually what happens is that all PageRank values will flow to F and G and the rest of them will become 0. I didn't show the whole thing, but if you do one more iteration, here it is. Look at the bottom of this. So 7 by 32, right? This is already getting more. And 3 by 16. 3 by 16. Is it already more than 3 by 16? 6 by 32. Right? Okay. So it's already more. So you keep doing this, they will get it. Is that okay? So now we have a problem. We need a way out of this. That if some guy is going to suck all the PageRank values by cheating, we need to get out of it. So the way we do it is like this. Okay. We'll choose a scaling factor called S, which is strictly between 0 and 1. Okay. Then what we'll do is that we will update the values just like we do usually, and then we will scale the values down by S. So typically S is a large number. So let's say S is 0.9. 0.9. So what we'll do is 0.9 we will scale so if once we scale down the values by S, that means the sum of all the page ranks in the net will become 0.9, not 1, 0.9. Okay. Then the remaining 1 by S I will divide equally among all nodes. No, it doesn't become strongly connected, but at least I want to make sure that it doesn't suck everything to itself.
So like from each node we can, with some probability, it may be less, but with some probability from each node we can randomly go to any other.
No, we are not doing that. We are equally dividing, we are taking remaining 1 minus s, dividing it by n and giving it to everybody.
Yeah.
So initially we gave 1 to everybody. Now we are giving, initially we gave 1 by n to everybody. Now we are giving 1 minus s over n to everybody. Okay. And this approach also thankfully works. Okay. And we'll just understand this. So s is, let's say I take 0.8. Yeah. Remember, s can be a large, generally in practice it's taken to be a large enough value. Yeah. So what I do is I'll do all these things, and then in the sum, in the final step, just do normal things. In the final step, in the sum, you make sure that you divide every value by, or multiply every value by 4 by 5. Okay. So then the sum total should be 0.8, because that's the s. Because now instead of having all of them sum up to 1, it's going to be sum up to s. Okay. Then, now 1 minus s is 1 by 5. Now I am adding 1 minus s over n, this much to every node. Okay. And turns out that this trick, we'll see, is sufficient in terms of getting us out of this problem. Okay. So we do this now. Look, it's got 18 by 80, 14 by 80. Let's keep doing this. Okay. But you can see that A is already more than F and G. So that's showing that it will not be able to cheat it beyond a point. Okay. So this is again stuff that you have heard before, but I just wanted to give you a quick pictorial view just to see how it's happening. So one nice analogy that I've again seen in the same book, which says that, look, it's like this, that if I want to imagine this as some fluid or rainwater flowing through all these things, if there is a sink, then I'm making sure that at least some of it is evaporating and coming down as rain to everybody, so that nobody is left dry. Yeah, that's a pretty neat picture. Are we good, guys? Yes.
So we saw another technique of list hubs and authorities.
Yes.
Where we do not have those separation of
Yes, exactly.
authorities itself are connected.
Yes, that's correct. So, yeah, exactly right. So the way to imagine this is that so here we looked at it as if somebody put a query like newspapers and we got these guys, right? Now in the concept of PageRank, we said I don't know what the query is, I don't know anything. So for some topics, this may be getting incoming. For some other topics from somewhere, this guy may be getting some incoming, who knows, or from somewhere else, right? So you just imagine a strongly connected graph. I actually don't care which topics are being talked about, and I just do this. So in a way, maybe you want to think about it as that if you have a topic, then I mean, you can still do hubs and authorities maybe without having the notion of a topic, but it's helpful to think of a topic in the context and then think of hubs and authorities being separated out.
Like when we are building, for example, we have to first of all get this linked graph to apply the algorithm. So
Say that again. We have to make the
graph first.
We have to make the graph first.
So for example, on the page, like how do they do it? Like for example, if I have something in my query, so only the
No. So first of all, there is a crawler, right? There is a crawler, and that crawls 24 by 7, and actually gets the directed graph and puts it in a bunch of like data warehouse that they have.
okay, so like is the structure of the graph independent of what query I am?
Correct. So, well, yeah, that's true. So I should be careful because I will have to check that.
For example, I am
So it's a combination. So wait a second. So PageRank is so today's, if you talk about today it's going to be, this is just the essence of the algorithm of how these values go. This is no means by the only thing that is done. So you would of course have things like keywords mattering, things like, I'm sure there are like, 50,000 other factors which are into this. So I'm not really, I cannot comment on that because I don't know what those factors may be. But I can tell you this, that these are not the only two things. It's not just keywords and this that will decide the value of a page, for sure.
So I think they regularly keep on improving their algorithm.
Yeah, and they keep changing it because people are always finding ways to cheat it, right? So that of course keeps happening. True. Yeah, but I hope the essence of this thing is clear. Yes.
So, after we do that, distributing 1 minus s to everyone, how does that guarantee that the sinks will not have the highest amount of liquid in them?
Yeah, I'll have to look that up and tell you. I don't know where the guarantee comes from.
You can think of it as, like I was saying before, if you look at the adjacency matrix, or for example, if you have a directed graph, and it need not be strongly connected, right? But we can think of S as a probability that, for example, if I am just going through all the pages and randomly I get bored and I just jump to anywhere else. So, we can think of,
I get that, but how does that?
So because with some probability I can go from one node to any other node, right? So the adjacency matrix can be thought of as a superposition of the original graph which is embedded and the adjacency matrix where each node is connected to every other node with equal weight.
But see, if I'm going with equal probability to any other node, then the probability of all the nodes are getting up the same amount, right? So my relative ranking should remain the same.
So there are two parts to this. Number one, that we don't have to think of it as random walk because whatever the remaining fluid is remaining, we are distributing it equally among all of them.
Right,
So it's not just one random jump. That's first part. Second part, what Shubham is asking is where do I get the guarantee from?
Okay.
Right? So I don't know the answer to that right now. I'll definitely respond and figure out and get back to you on that.
I think the guarantee comes from the fact that because from each node we can go to any other node.
From each node, see, it's
The original theorem stated that if we have a strongly connected directed graph, then
Yes.
this will converge.
yes, yes.
Now
Now we don't have a strongly connected
we
graph.
don't have a strongly connected.
Correct. So now what we're doing is we are actually saving on some of the fluid, and the saved fluid we are making sure we are distributing it equally,
Yes. So
right? So for the okay, you go on.
For example, we have this graph. Just for example.
Yeah.
So these edges are the original edges of the graph.
No, wait, no. Let's go to a.
So for example, if we have this graph and
Huh. Now tell me. Now we have this graph.
so the S factor that we talked about.
Yes.
We can think of it as this. For each of these edges, I give it a weight of S.
Yes.
Which is generally
Yes.
it's a large
Yes.
number.
Yes.
Now on top of this graph,
Yes.
I have a fully connected direct
Yes.
graph,
Yes.
which has a weight 1 minus S.
That's true. That's true. Hold on. 1 second. Hold on. Yeah. That might just work. Yeah. But I'm giving it to every node, and you're saying it to everybody. But I can.
Strongly connected graph, complete direct graph with n square edges.
Yeah. 1 second. With n square edges, but the way it is done is that every node is getting 1 minus s by n. So I have to make sure that I divide it among the edges accordingly.
How is it a strongly connected?
No. Yeah. So what he's saying is, let me just rephrase what he's saying, and you can tell me if I'm rephrasing you correctly. So what he's saying is that one part, everybody is connected to everybody else, and there are some numbers here, x1, x2, whatever, and the sum of every row here sums up to s, right? And if you do it all across all rows, you'll get n times that or whatever. Now he's saying plus this part here. This part here is the completely connected part, so we know it's strongly connected because instead of saying that I'm going to shower all this 1 minus s by n to everybody, I'm saying that this whole graph is completely connected where a small part is going from everybody to everybody else. Okay?
Everybody
No,
Everybody.
because what did everybody, because what did I do? I saved 1 minus s and showered it equally on everybody. Right? On a node. I describe it as a node activity.
That's a
Right?
minus
Now what he's saying is treat it as if it's an edge activity such that this guy is a completely connected graph, and if I look at this guy is getting something from himself, something from here, or whichever it's going, such that this sum is now 1 minus s over n. So what is happening is by adding this component, I am preventing the original graph. I mean, I'm making it strongly connected because by adding, I'm treating it as if now the graph has, since I have a full weight, part of the weight I'm saying, okay, this is the graph where it's not completely connected, meaning it's not strongly connected, and then I'm adding a complete portion to it with a smaller weight, but by adding this component, I'm making the whole thing as strongly connected. I'm cheating.
Yeah, I get that it's strongly connected, but I'm not entirely convinced that every node is connected to every node, because
No, that's the way we can reinterpret it. See,
if I reinterpret it,
huh.
then from the sync node, what you're doing is basically like distributing it all equally to all the other nodes.
That is done for each node.
No, for everybody, not just from, see, so if you forget about how Pujan is, interpreting it, what we are doing here, let's first talk about what we are doing here. So what we are doing is, whatever that remaining value is, I'm dividing it equally to all the nodes. Since I'm dividing it equally to all the nodes, I can pretend who's the person who's giving. I'm the central guy who's giving. He's saying, no, let's treat as if every node is giving to every other node. Sorry, now you go on.
Yeah, but we do that only when we have a sync, right?
No, this technique, by the way, will work even if you have a strongly connected graph.
Oh, so you do that.
You can do that anyway.
You do it.
Do it anyway so that you don't have, because where will you sit and check whether this, because the real graphs are quite often have disconnected, the real World Wide Web graph, as we saw in that other telecom thing, it will have disconnected components, it has in, out, the ways so there's lots of stuff that's actually happening.
So by design, you make it complete.
By design, exactly. Yeah, so that answers our question. Yeah, the guarantee part I'll get back to you. Any other comments or questions at this time? Okay, so then I'll move on to the next. Okay, so now let's talk about. So we heard about balance, right? Balance. I think Professor Sinha definitely talked about it. I don't know if Professor Santanam talked about it, but I don't think he did. So what we are now interested is we are interested in graphs which have a sign on the edges. Okay, and maybe a simple thing is to say, I go and ask everybody and their friends what is their opinion on a certain topic. And let's say that there are only two opinions on the topic, and if two people, who are friends, and if they agree, then we say, look, the opinion of Cassie and Dan is agreement, so I'll put a blue colored edge between them, and if they disagree, I'll put a pink colored edge between them. So that's how I can get my signed graph. Okay, these things are called signed graphs. Okay, and the fact that there is no link means that there's no really no interaction between these guys. Right? In this case, I can, by looking at this graph, I see that clearly, since Dan agrees with Cassie and Eve, they can be put in one group, and Alice and Bob, since they seem to be disagreeing with the other three as a group, sort of, then I can put them both in one bucket. Right? So I can divide this into two parts: one which thinks that they are all, in agreement with this thing, and the other ones who are in disagreement. Right? And this, of course, is numerous applications. So if you see this picture, it's historically tracing so while I talked about agreement and opinion, you can also interpret these edges as being like, dislike, or friends, enemies, whatever kind of thing. And this actually says how the alignment between these countries, Great Britain, France, Russia, Italy, Germany, and Austria, World War I, and so on. You can see how these alliances were changing and evolving over a period of several decades. Yeah, so you can see that you can use this kind of depiction to understand these scenarios. Now, the Now there are things like slash dot and opinions. Have you used any of them? Anybody used any of them? Slash dot. Have you seen slash dot or opinions? So anyhow, on slash dot, users can actually designate each other as friend or a foe. So you can make explicit plus minus links or blue pink links between people. And on opinions also, users can express different products, evaluations of different products, and also express trust or distrust of others. So if you think about trust, I trust you, and you trust, I trust her, she trusts you. Will I trust you? Will this be transitive? So there are lots of settings in which you want to understand, right? Or if I distrust her and she distrusts you, will I trust him or will I distrust him? There are no clear answers, but people are of course doing studies all the time to see whether in a particular network or under a certain set of assumptions, is this more likely to happen, less likely to happen, and so on. But here right now my point is only to convince you that these are practical applications of this theory. Yes? Okay. So now we'll come up with the notion of something called balance in signed graph. So first of all, these graphs are signed. Signed meaning every edge that's there in the graph is actually has a plus or minus label. And now we want to see what is balance. So we say that a cycle is balanced if it contains an even number of negative edges. Okay? Think about that. Even number of negative edges, because we are saying that A is disagreeing with E is agreeing with D is agreeing with B, then B better disagree with A. Yeah, I want you to be convinced of the definition. Yeah, that a cycle is balanced if it contains an even number of negative edges. A graph is balanced if every cycle in the graph is balanced. Okay, so if you look at the graph on the right, then let's look at this, right? This is not balanced, but it's not so difficult to see. So what we are saying is, so let's say there are really two interpretations. Number one, if I think of them as being about an opinion about a topic, then it's impossible that if A and B agree and B and D agree, then A and B disagreeing doesn't make any sense at all, right? So this is why we call it unbalanced. If I look at as like-dislike, then what we are saying is that A likes D, B likes D, and A doesn't like B. Entirely possible, but it creates a lot of stress on D. So that's why the situation is not a happy one. Right? So D has two friends who are not friends with each other, not good, right? So okay, the same holds for this. Okay, so now we know that what is an unbalanced graph and a balanced graph. So if I want to see whether the graph is unbalanced, I need to see if there is any cycle which is unbalanced in the graph. Yeah? Yes. So there are two interpretations. Either we can say that there is some topic on which they both agree with each other, or I can say they like each other.
I see. So then basically what we are saying is we need that so that this relation becomes transitive.
I would not transitive. We want to make sure that it becomes consistent. So if I think of it as an opinion, so let's say that A and B disagree, A and E disagree, right? B agrees with E. Okay, just bear with me for a minute. It'll become clear. The point is that let's say that A and D agree on an opinion. Okay, let's say I ask them that do you want to have tea in the morning? Okay, so A and D say yes, B and D say yes, then A and B can't be in disagreement with each other, right? So you have a situation which is not consistent. It doesn't have a consistent interpretation. So if I think that I'm interviewing all A and B on some topic about a certain thing, then I get a consistent labeling or I get a consistent thing only if all the cycles in it are balanced. Okay, but if I go with the other interpretation that this fellow likes this fellow or not and all, then it's a little bit of a hazy fuzzy thing, but I can still say that D is under stress. Yeah, D is under stress because D is under a lot of stress because same thing is happening with A and D as well. right? So whenever a signed graph is balanced, what is balance? Will somebody just say it again?
Each cycle is an even number of.
So a signed graph is balanced if
All the cycles.
all the cycles in it are balanced, and a cycle is balanced if it has an even number of negative edges, even including zero, right? So now when that happens, I can actually divide the graph into two parts. One is two parts in the terms of vertices. Okay, remember for balance, for signed graphs, we are only labeling the edges. But based on this, we can derive a labeling on the vertices. We can say, look, the vertices of a balanced graph can be divided into two sets, such that one set is all blue, the other set is all pink. Okay, and of course, every plus edge will be such that it'll connect two vertices in the same subset. All the so I'll imagine that there are two sets here. All the edges here will be plus, all the edges here will be plus, but only things that go across will be minus. Okay. All right. So let's see how I would do this. So let's say I've got this. Somebody has given me this graph. I'll say, look, I'll arbitrarily start at A, and I'll call A as +1. Okay. If A is +1 and A to B is a +1 edge, I'll just treat it as a +1 number. Then B will be +1 multiplied by +1. I will get B also plus, so B becomes blue. Right? So this I've written like this, that S of A, S is the label, the sign on a vertex, not an edge. Yeah? And we are saying that SB is SA into S of A plus multiplied by S of AB. Now this sign is of the edge, this is of the vertex. Right? So +1 into +1, +1. So B gets the same color. C will get this, C is going to get minus, because that's +1 into -1, because that sign on that edge is -1. So +1 into -1, -1. So the sign on C becomes minus. Are you with me, guys? Yeah. Now look at D. D is -1 into +1, so it will also get -1. And E is -1 into +1, so it will also get -1. And we can check that minus into minus is plus. So this is actually done, because we know we have a balance cycle, and so we know that we have nicely put the vertices into two buckets of blue and pink.
This is a lot like in that if you have a graph and all the cycles in it are of even length, then it is bipartite.
Correct. Something like that. Yeah, something like that. Yes. Yes.
Divided into two groups. AB is one group and EDC is another group. But what was mentioned is each edge among the group should be a positive edge.
Correct. So now if you see, correct. So that's correct. But every positive edge will be in that group. So it's not completely connected. So we are not talking about completely connected graph, but this can be. So we can, it'll easily generalize to even that case when it is completely connected. There all the positive edges will be there. Okay. So now what you notice that this group has one positive edge. This group only has two, out of a maximum possible of 3. Right? But all the edges will only go across. Okay? Whatever positive edges there are will lie within the group. Either this group or that group. Whatever negative edges there are, they will be across. They can't be inside. That's the point. Okay? And we'll see this even more clearly. So now let's try with some other graph with this kind of labeling. So A is, let's say arbitrarily I'll call it positive. Right? Then B will become plus, so B becomes blue, C becomes pink, therefore D becomes pink, therefore E becomes pink from this side, but now it's not consistent with A. So I can't assign a color to E. And now I know I've ended up with a unbalanced graph, because if it were balanced, if every cycle was even number of negative edges, then I would have been able to do it. But this shows that I'm not able to do it. So since it's an unbalanced graph, I therefore cannot assign the entire set of vertices to two groups and neatly separate them. I cannot do that. That's the point. Yes? All right. So what is this, guys? Can you tell me? The guy on the left, is it balanced or unbalanced? What about this guy? Right? So these two graphs are balanced. Now, if I want to interpret this as like dislike, can you explain to me why is the second one balanced? A and B are friends, they have a common enemy. No problem here, no stress. Yeah? So like you guys correctly said, both these cases are balanced, right? Now will you tell me about this, guys? Both of them are unbalanced. Why is that? Because you can see that this got an even number of negative edges in both the cases, right? Odd number of negative edges. Yeah? So that's why these both are unbalanced. Yeah? Okay. So let's see. So if I want to say this in English, it seems like I can achieve balance in two ways. Either everyone likes each other, it's all plus. Yeah? The world is a happy, peaceful place. Or the world consists of two groups of mutual friends and complete enmity between those two groups. Right? So, right? And these are the only two ways of having a balanced network. That's what seems to be the case. Okay. So there is, in fact, we can actually say it out as a theorem, is that if a labeled complete graph, I'm now saying complete graph, that means every pair of vertices has an edge between them, and that edge has a plus or minus label on it. Every edge has a label on it. Then all the pairs of nodes are either friends. That means it's all plus edges. There is no negative edge in the graph. Of course, in that case, I'll just get one component, right? Otherwise, I can divide the graph into two groups such that every pair of nodes in X like each other and every pair of nodes in Y like each other, and everyone in X is the enemy of everyone in Y, right? So I'm saying that if everybody is just saying, look, so does this remind you of something? So I go to ask everybody and I say, look, do you like this guy, do you like this guy, and so on, right? And then everybody tells me whom they like and whom they dislike. Then I zoom out and I see that the graph, assuming that at least there is one pair of people who dislike each other, I'll find that the graph falls neatly into these two groups. Does this remind you of some other discussion we had recently? Local properties to global properties, right? When we said, I'll ask you, is this a weak link or a strong link? Then we saw that this is very well connected with the idea of a local bridge. And the idea of a local bridge was more of a global property, whereas the weak and strong ties were a local thing. Right? So here locally I'm interviewing like, dislike, and suddenly I say, outside when I see the global structure partitions the graph into exactly these two things. Okay? Now, let's see if we can prove this thing. Okay? So now, if you see, A has a positive link with B and C. Right? What are the possible labels that BC can have? Positive. Yeah, the question is what is this graph? This signed graph is balanced. The fact that it is balanced, okay, I'm going to use the fact that it is balanced to prove something about this. So, if A has a positive link with B and a positive link with C, what is the label on edge BC? It can be either plus or minus. There are only two things. What is it going to be? Plus. Why is it going to be plus?
Because the cycle should have...
Because if I have it negative, I'm going to get an unbalanced cycle. Then my assumption that the graph is balanced is gone. That means that BC has to be positive. Right? Are you with me, guys? That means that, and of course BC, ABC are just arbitrarily anybody. This means that every link in this friends of A have to be friends of each other. They have to be friends of each other. Okay? What about D and D? So D and D are enemies of A. Okay? And the edge between D and D can be either positive or negative. What will it be? Positive. Positive, huh? Positive, negative? Positive. Why will it be positive? Because it's a balanced graph, the cycle should have an even number of negative edges. If I add one more negative edges, it becomes odd. The assumption that the graph is balanced is gone. So even those edges are positive. So what it tells me is that BC and DE have to be positive, right? And BCD is only a template. So every edge in the friends of A should be friends. Every pair of enemies should be friends with each other, among themselves. Now let's ask the final question. What about BD? A is a friend of B, A is an enemy of D. What should be between BD? Negative edge. Because that's the only way I'll get a balanced cycle, right? And the moment I do this, I've actually shown that every edge within a group is positive, every edge across is negative, right? And with that we have proved. And this is actually quite even more striking than our weak strong example where the local bridge was it was a global thing, but this is more strikingly global than even that example, right? So this is, from my perspective, the thing about, what I say, the fact that we have a network, this is the thing that always sort of interests me, is that we are able to, since we have an explicit network, we can model local processes and measure the global impact of it like that, right? This proof is exactly what you guys taught me, right? Which is saying that BC must be positive, DE must be positive, BD must be negative. Everybody convinced? This is the balance theorem and you guys just proved it. Yeah? Okay. Right? So again, right? So this is like bridging this or always thinking about stuff from a local and global perspective. This is a good theory which actually lets us do that. So it's kind of, somehow very satisfying. Yeah? Pleasing. Now, let's talk of a slightly related problem, and I'll try to go through this quickly. Is that now let's see if we can balance unbalanced graphs. Okay, so we are given a graph that is not balanced, and we want to balance it. Now, there are really two operations that I'm allowed to do. Number one, I can either flip the color of the edge, or I can just cut it out. Okay, so for example, if I have this graph on the left here, which is unbalanced, I can balance it either by making this AD edge, changing it from positive to becoming negative, or just cutting it all together. Okay, this is how I would balance an unbalanced graph. So what do we know about these things? So what we already know is that if there is an optimal minimum size for flipping and there is an optimum minimum size for deleting, then those answers are actually the same. Okay, if they are indeed the optimal ones. And of course, actually finding the optimal one is hard in every sense of the word. Okay. All right. So what we'll do is that we'll try to find ways of we'll try to find heuristics which help us somewhat.
Checking if a graph is balanced or not can be done in linear time.
Yeah. So how do you do that? So how do you check if a graph is balanced? So you first, you first find a spanning tree of the graph. Okay. So in this picture, all thick edges are tree edges. Yeah, spanning tree edges, and all the dashed or dashed ones are in fact non-tree edges. Non-tree edges. Okay. So what can I do? And now I can assign. So first of all, I've fixed a rooted spanning tree of T to find any tree. Yeah, and then arbitrarily assign the root to be plus, right? And just based on the edges that you have in the tree, you will get a clearly consistent labeling, right? So if the thick edge is blue, C will become blue, and if the edge between C and B is pink, then B will become pink, and from A to E is pink, so E will become pink, and E to D is blue, so D will become pink. You see that, right? Of course, you just as an aside, if I flip both the colors, I'll still get a consistent labeling. Right? So every blue guy could be pink and every pink guy could be blue. It doesn't matter. Actually, it doesn't matter, right? But you see that. Now what do I do? Now I look at all the non-tree edges as well, one by one. So I will look at triangle ABCA. Now remember that if you have a spanning tree and if I have all the non-tree edges, each non-tree edge will make a fundamental cycle. And so I can examine every fundamental cycle one by one. So I'm going to look at the first one, that is ABCA. Now ABCA, I find that A is positive, C is positive, B is negative, and the edges labeling, you can see on one side it is +1, the other side it's -1. So if I multiply the two, I get -1. So this label on this edge is -1, that is consistent, so I'm good. Right? What am I checking? I'm checking is S of AB, the sign on AB, is it in fact a product of the labels on the two vertices, endpoints? Right? So I should actually put a question mark. Is this sign, in here it is -1, is it same as, and SA is what? SA is +1 and this is -1. So if I multiply these two on the nodes, on the vertices, and I see that the current labeling of the edge is consistent with this, so that's why this is good. Right? Now I go to the next one. What is the next fundamental cycle? I say ACBEA. Okay? ACBEA, what do I see? I see that, okay. So BE is the edge. And on the edge it's -1. SB is negative, SE is negative. So -1 into -1 is +1, but the edge is negative. So I got a violation. This is enough to tell me that the graph is not balanced. That's enough. So I don't even need to go to the next one. Okay. So I can check that a graph is balanced or not fairly easily. Okay.
Implementation wise, again, I find a lot of similarity between this problem and checking if a graph is bipartite or not. So like we can just choose a node and perform use a queue to perform a breadth first search and keep on checking while we are doing it. That will easily work.
So here the process is that you first build a spanning tree.
So like
Then you cycle through each non-tree edge.
yeah.
Okay. You do that in bipartite graphs?
No.
So like what I'm talking about is, for example, if I have been given a graph and I want to
Check whether it's bipartite or not. Okay.
balance or not, any of these two.
Uh-huh.
So what I will do is that for example in breadth first search we use a queue to keep track of the layers, right? I started a node, okay, and randomly assign it one of the two, +1 or -1. Then I also mark it visited. Then I push all of all the adjacent nodes which are not visited into a queue and check if for example, with each edge I will have a number +1 or -1. So if let's say the original node was 1 and the edge was also 1, then I will assign 1 to it.
Oh, I get it. Yeah, okay.
And
Okay.
that will just,
Okay.
If anywhere there is a contradiction,
Yeah, I got it.
we'll say that it is not balanced. And if there is none, then that assignment itself is a balanced assignment.
We're going to say something more, Mano?
In some other sense, it's exactly checking if it is bipartite.
Yeah.
You can do a coloring.
Yeah.
idea.
Yeah. Because a bipartite graph has two colors.
Two colors.
And you should have all cycles of even length.
You probably start here.
Right?
The same way.
Yeah, sure.
Color it and color all of its children which are not visited.
Right? Okay, so what we are going to do is we are going to check, we are going to try to have a heuristic which will try to find the smallest number of edges, because it's a hard problem, to find the smallest number of edges to flip to balance G. Okay. Now, this was a paper published in 2021, and what they said is that, look, let's use this idea of this get a spanning tree, and then decide which of those edges need to be flipped. So what do? You take a spanning tree. Now look at each fundamental cycle one at a time. Okay. So here you look at ABE first, and you see that this is actually unbalanced. So that means I'll flip BE. Okay. Why do I have the confidence that flipping B will not change anything else? Because it's a fundamental cycle and it's with respect to the tree, so it actually works out. So we'll think about that also in a bit. Okay. Changing that doesn't affect anything else. That's what you need to convince yourself. Okay. So if I flip BE, then ABE will become balanced. Then I look at ABCE, right? ABC is going to flip CE, We'll say flip C because again this has 3 negative edges. I need to flip it. Right? Then I look at A, B, C, D, E, the whole cycle, and I see that again there are 3 negative edges. I flip C, D. Okay? And now I look at A, B, D, E. It has 2 negative edges. I don't need to flip it. I don't need to flip it. Now I look at this. You'll see that everything is balanced, and because it's balanced, I'm able to divide the set of vertices into 2 colors. Okay? So this is balanced. So this was their technique. Okay? That we can just use this to figure this out. Right? So what we thought is that maybe what we can do is that instead of just flipping, so if you flip the number of non-tree edges, so first of all, how many edges are there in a spanning tree? N-1. The number of non-tree edges may be actually far more than n-1, right? So the idea is that if you can flip some tree edges, so in one shot, if you can fix multiple things, maybe it's tempting to try, right? So what happens is that for every unbalanced cycle, in the case of in the case of AL21 algo, I have to flip that many non-tree edges. Here we are saying, okay, suppose I allow flipping tree edges, can I get lucky? That's the question. Why? Because I want to reduce the number of flips. And remember, our goal is to balance an unbalanced graphs using as few flips as possible, right? And that we know is a hard problem. Right? So we have this notion of, we will say that a tree edge UV, it covers non-tree edges whose fundamental cycle contains UV. So if you look at the edge AB, it covers BE, right? It covers ABDE, that means it covers BD, the non-tree edge BD. It covers the non-tree edge CE, and it covers the non-tree edge CD as well. Is this clear? Right? What do I say? I say that a tree edge covers all non-tree edges whose fundamental cycle contains that tree edge. Why am I doing this in the first place? Well, I'm seeing if I flip this tree edge, in one shot I may be able to balance many non-tree edges, because I'm trying to cut down the number of flips. Are you with me, guys? Guys, are you with me? Say something. I know I'm standing between you and lunch. Yes? So, now I want to see which are all the edges, non-tree edges, that are being covered by AB. That means, suppose I flip AB, B will be affected. That's all I'm saying. I'm not saying whether B is balanced, not balanced. I'm not saying that. I'm saying that if I flip the tree edge AB, the triangle which is formed by AB is going to be affected. Yes? If I flip AB, the rectangle formed by ABDE or quadrilateral is going to be affected, right? Which means that the non-tree edge BD is going to be affected, right? And this is going to be affected. Similarly, CE is going to be affected, and CD is going to be affected, right? Now, how do I decide whether I should flip it or not? So now what I see is that, look, BE, this triangle is unbalanced. This one is balanced. Right? This one is unbalanced. This one is unbalanced. So, in the sum total of it, I see that if I flip this AB, then this AB triangle will become balanced, but ABDA will become unbalanced. They will all flip. Balanced ones will become unbalanced, unbalanced ones will become balanced. Okay? So, is that really a good idea? So, well, what is the intuition? Well, we'll say that, you know what, if I'm getting more good out of it and I'm doing only a little bit bad, it's okay. Let's see how far we can go with this. Okay. So, you just say something called gain. That means how much good I do minus how much bad I do. That is how much benefit I'm getting by flipping this tree edge. Okay. And so this is the idea, that you just start with one of these guys. Find that which is the one that is giving you the maximum benefit. Pick that guy. Pick that guy, flip it. Now some things will go good, some things will become bad. But you are sure that there are fewer bad things and more good things have happened because you have checked that the gain should be greater than 1. That gain, what is gain? Gain is this thing. More good than bad. More good than bad, right? So basically this idea works out, and if you have a thing like this, then you see that which is the one by flipping which I'll get the most benefit. You'll find that 13, 14, the guy in the center. Now which are the unbalanced cycles? I'll show you the unbalanced cycles. This is an unbalanced cycle, 1, right? This is an unbalanced cycle, 2. And this is an unbalanced cycle, 3. And of course there are similar things, 3 times whatever, 4 or whatever, you will see on the other side as well. Right? So there are that many unbalanced things. Now, so right. So the best one is to flip is 13, 14. Why? Because if I flip that, then at least look, this guy will not be affected by it. Right? These guys are not affected. But these 4 big ones are. Which are the 4 big ones? X1, X2, X3, X13, 14, X1. X7, X8, X10, X14, 13, X7. X4, X5, X6, X13, X14, X4. And X10, X11, X12, X14, X13 and X10. Are you with me? Right? So the gain is 4. It does not unbalance anything. It balances 4 things. So I will pick it. And the moment I pick it, these 4 guys got nicely balanced, so I'm showing them in green. But I'm not yet done because I see still more negative things are remaining. So I keep doing this. I go to the next one. The next I'll flip is X2, X3, X5, X6 and X6, X8. Just convince yourself that if I flip X2, X3, I'm going to get these two. If I flip this guy, then this one and this one, they both will get balanced. Right? So I will flip it. The moment I flip it, these two become green. Similarly, by symmetry, you can see that I'll do the same thing over here, and I'll do the same thing over here, that will happen. Okay?
X12 and X11 should also be.
Correct. Why are they not done? Because if, now what do I see? X11, X12 if I do, I'll get a benefit of 2. But suddenly, meanwhile, what has happened is, X13, X14 have again seen that 3 of the other edges have become negative. Because what happened was, as these guys started, as we made X2, X3 to, from blue to pink, the outside green one started becoming pink. Okay, why? Because now X1, X2, X3, X13, X14 and X14 to X1, that now has an odd number of negative edges. Right? And so for the 3 guys it was okay, but the moment these 3 guys got switched, X13, X14 got the maximum M again, because now flipping it will give you a benefit of 3 edges, whereas flipping X11, X12 gives me a benefit of only 2. So who gets picked? 13, 14 gets picked again. Right? And when 13, 14 gets picked again, it becomes blue. And then of course we have this situation. Now X1, 11, X12 is again going to be the guy with okay, right? Now X11, X12 gets flipped, and now we have everything that's resolved. Right? So now what happened is that the algorithm actually chose X13, X14 twice. Since it was chosen twice, it means it doesn't require flipping. Right? So it'll work like this, and this actually turns out to be that this is the optimal one. Okay? So it turns out that sometimes just by flipping a tree edge, you can get a lot of benefit. So for example, if you have a graph like this, and if you flip non-tree edges, you might end up flipping order n square non-tree edges. And if I mean, this is of course an extreme case, but it can be as good as this, that you, with one tree edge flip, you can make up for having n square non-tree edge flips. So you'll get a smaller number. Okay. Okay, thank you.